So critical values, by the way, do not require the sample mean because we are going to compare the critical values with X bar. So when we calculate the critical values, X bar is not required. So the answer is one of these three. And according to the formula, your belief is around 100, 100 minus, plus minus, and by the way, so 5%, we are using significance level 5%. So you have to use 1.96. So top 2.5% value is 1.96 when you write it as a cumulative probability. It has to yield 97.5%. So 1.97 is the z-value corresponding to 5% significance level. And sample size, standard deviation was 5. Sample size is 100. So plug in the numbers, you are going to get these numbers. It was a simple exercise, but let's think about this now. The reason why we are calculating the critical values is to understand type 1 error. So our objective is to calculate the probability of type 1 error. So remember, it's defined as the rejection of H0 when it is true. So basically, the probability of type 1 error is the probability of rejection. And rejection happens when this happens, when the sample mean is too small, smaller than the lower critical value, or the sample mean is too large, greater than the upper critical value. So this is when rejection happens, and this is when potentially a type 1 error would happen. So if you don't reject, type 1 error never happens. Type 1 error happens only when you reject, right? So think about this. So probability of type 1 error is probability of these happens. Either too small or too large happens. So we have to calculate this probability in this way. So this is probability of type 1 error. I use the conditional notion, conditional on mu equals to 100, because type 1 error was rejection of H0 when conditional on H0 is true. So H0 is true means the mean was 100. So that's the reason why I condition the probability on mu equals to 100. So this probability is type 1 error probability. You have to calculate this, and maybe now you have a good idea how to handle this. The randomness is coming from X bar, and we know the sampling distribution of X bar. It's approximately normal distribution. So you are going to standardize these guys using the sample, using the mean and standard deviation. So you are going to calculate this probability. This is the probability of rejection when H0 is true. Probability of rejection given that the null hypothesis is true, and critical values are already fixed. We calculated the critical values, so plug in the numbers, and then standardize the X bar to a standard normal distribution. So 99.02 minus the mean of X bar, and we know it is 100 because we assumed it. We already assumed that H0 is true, the null hypothesis is true. So you use that for standardization. And denominator is the standard error, which is the standard deviation and sample size. And if you do the math, interestingly, what you are going to get here is this guy equals 1.96, and this guy equals to 1.96. The reason is, briefly, do you remember how we got these formula? Or when we calculate, when we derive the critical values, we used standardization there. So z alpha over 2 and s over square root n came from the standardization during the derivation of critical values, and we are using the same standardization again. So it goes back to, so if you subtract mu 0 from the critical value and divide by standard error again, then you are going to get this. If you standardize this again, will be cancelled out, and this will be cancelled out, and you will have the z value only. So in the end, it becomes 5%, which is the significance level. So this holds all the time. All the time. In some textbooks, this is the definition of significance level. So some textbooks explain, I introduced significance level as the threshold, your standard of rejection, but some textbooks introduce the significance level as the probability of type 1 error. Both are correct. That's also correct. So you may understand it as this. So in the previous chapter, I explained when you choose significance level equals to 5%, it means that you are going to reject the 5 most suspicious customers. That's how I introduced this number. And if you want to reject more, choose 10%. If you don't want to reject many, then choose 1%. So it's your choice, depending on how much you want to reject. But also you may explain the same thing using type 1 error. So when you choose 5%, that means you admit that some innocent people were banned in our previous using the reservation example. So some innocent abusers, some innocent customers can be banned, treated as abusers, and that probability is 5%. If you can sacrifice up to 10% of innocent customers, then you can choose a significance level to 10%. If you don't like the collateral damage, the making innocent customers as abusers, then you can reduce this significance level to 1%. So anyhow, the choice does not change, and the principle and the intuition does not change. It's how you interpret. It's a matter of how you interpret the significance level. I just used the strategy that significance level is the frequency you desire, how many rejections you are going to make, and then it happened to be the probability of type 1 errors. But excuse me, you may take a different interpretation. Anyhow, the significance level equals the probability of type 1 errors. Without any algebra, you don't need to do any algebra to answer that. Here are a few comments. Standardization uses the true value of mu, and we assume that the truth is H0, right? And later in a few minutes, we are going to use different assumption here. Then your standardization will be different. And second, so far, I did not tell you what's the value of x bar. X bar is treated as an unrealized random variable. As I mentioned in the earlier slide, critical values are used. It's convenient, particularly convenient when you use the same critical values again and again for different random samples. Like for example, in this example, if you can use the samples, the same critical values to different brands of diabetes drugs, then 5% of brands, 5% brands will be rejected by mistake, by error. So that's so anyhow, what we don't need a specific value of X bar to calculate the probability of type 1 errors. So you can think it this way. Before actually rejecting something, you calculate, before you observe and calculate the sample mean from the data, you can estimate, you can predict how much type 1 errors will happen. That's in the end, that's significance level. And so in that sense, X bar is not realized yet. It is just an unrealized random variable. Still, there is no problem. It is random. As long as it is random, it does not matter. So simply speaking, type 1 error probability always equals the significance level. And when you increase alpha, when you increase higher alpha, the higher the significance level is, the more likely to reject H0. That's what I explained in the previous chapter. And because you are making more rejections, you are more likely to make type 1 errors, because type 1 error happens when you make a rejection. And in the modern legal system, usually type 1 error is considered more serious problem. So it is better that 10 guilty persons escape than 1 innocent suffers. So maybe Sir William Blackstone is a very famous, I don't know, but famous like legal researcher, I guess. So he said type 1 error should be considered more seriously. So that's why we restrict the significance level, and we use innocence as the null hypothesis, and we would like to control the type 1 error probability using alpha. So that's one possible, another way to interpret this. And now let's consider type 2 error. So I'm going to stop this video here, and in the next video I will continue to type 2 error, how we calculate type 2 error probabilities. See you in the next video. Thanks.